Today's speaker is Théis Bazin. He is currently a PhD student at the Sony CSL Paris under the supervision of Gaëtan Hadjeres, and he studies creative interfaces using AI for music technologies. And before that, he had a master in machine learning and statistics, and a master in music science. And so he will present about his recent work on spectrogram inpainting on interactive generation of instrument sounds. So the floor is yours.
Okay, thanks, David, and welcome to everyone. So the work I'm presenting here is done in conjunction, in collaboration with Gaëtan Hadjeres from the Sony CSL Paris lab and my supervisors at ICANN, Philippe Esling and Mihail Malt. So, and I will be talking about recent work that we did last year, this current year, on, as David said, spectrogram inpainting. So first, a rundown of the major contributions from this work, and then I'll get into the details. So in terms of the machine learning part, we have developed an efficient VQ-VAE plus transformers-based model that allows to perform inpainting, and I'll explain what inpainting actually is just right after that. So inpainting on instrument sounds, and this model furthermore supports global constraints such as setting the type of instruments one wants to generate or the pitch of the instrument that one wants to generate. We have then trained this architecture on the NSynth dataset of instrument sounds, which is a dataset that was released by the Magenta team at Google, and that is comprised of around 200,000 instrument sounds, each of duration 4 seconds, in a wide range of instruments. And finally, we have developed and we are open sourcing an interactive web interface for this model that you can see here on the right, called NOTONO. And this interface allows both researchers to test their own inpainting models of audio and that is the most interesting part for us at CSL Paris, allows musicians to readily make use of those new types of tools. But first, I will now introduce what actually inpainting is all about. And so in general, inpainting deals with reconstructing missing parts of an input media. So it could be any type of media. It has most broadly been applied to images, as you can see on the right. But in our context here, we wanted to try and see how it could be applied to audio. And so concretely, this idea of reconstructing missing parts is often implemented through an interactive masking approach. And so the user will selectively hide parts of the original input and then ask the model to reconstruct those missing parts. Statistically, it amounts to modeling local conditional distributions, such as, for instance, asking the model to compute the probability distribution for this pixel here, given the surrounding information. And because of this local aspect, those inpainting models are readily amenable to interactive usage, as you can see on this demo on the right that I'll play right now. It was made by people at NVIDIA. So you see here that the user on the left is progressively hiding more and more of the original image. And on the right, the model tries to reconstruct the hidden parts. And the more the original image gets hidden, the more different, naturally, the output becomes. And so in terms of applications to music, prior to the work that I'm presenting right now, we'd actually, here at Sony CSL Paris, already delved into inpainting for music, but only in the symbolic domain. And the idea there was to regenerate parts of a sheet given the surrounding context. So, for instance, asking a model to regenerate this measure here given the surrounding measures. And examples of models that allow to perform inpainting on symbolic music include the deep art model created by Gaëtan Hadjeres at Sony CSL Paris that allows to create 4-part chorals in the style of Bach, and also the more general anticipation RNN, also by Gaëtan Hadjeres, which is a more general recurrent model for inpainting of temporal sequences. And so the work that I did with Gaëtan 2 years ago was for a NOTONO prototype that you can see on the right, and for which I'll play a video just after. And it was an attempt at designing an interface that allows to use those symbolic inpainting models for in a professional music production environment. And yeah, let's see how it works.
The NOTONO interface displays a sheet with which the user can interact by selecting zones such as measures or beats. The model is then tasked with regenerating those zones by analyzing the surrounding content. The user can enroute the output of the interface using MIDI to Ableton and synchronize the playback of the interface with Ableton using Ableton Link. This allows to create loops and instrument sounds using Ableton, whilst still maintaining the ability to interact with the generated sheet using the NOTONO.
This allows for tight integration of the prototypes that we are developing within the standard workflow of musicians, which is the core aspect of what we are trying to do here at the music team at CSL Paris. That is that we really don't want musicians to have to dramatically change the way they work in order to use our creative prototypes, but we really want to make it as easy as possible for them to introduce the new techniques into the standard workflow. And so that was the results of the work that we did 2 years ago with Gaëtan in NOTONO. And now for this new project, we wanted to see how those inpainting approaches could work on sounds. And I now play a video of the resulting NOTONO prototype.
So again here, we start from within Ableton Live, where we have created a very simple drum loop. And we will be using our NOTONO prototype to create several sounds to add to this track in order to make it into a full song. So here it is, the NOTONO interface, where you can see a 4 seconds sound as a spectrogram representation with time on the horizontal axis and frequencies on the vertical axis. And we'll start by designing a bass sound. So for that, we first look for an initial sample that we like, say this one, and now we'll load it into the interface. We can check how it sounds using a MIDI keyboard. And we can start by now devising some constraints. So we say, okay, I want to generate the bass sound, so I'm going to select a low octave, and then maybe, okay, make it sound first like a guitar. And here the user can interact with the interface by selecting zones on the spectrogram using this grid. And the model then uses the current constraints and regenerates the underlying portion of the spectrogram by analyzing the surrounding information in the sound. There are different tools that the user can use, so for instance this random brush or this eraser, and all of those tools are inspired by tools commonly found in image processing software. Okay, so now we have created a sound, and we can check that it sounds right with the initial drum loop that we had. So we go back to NOTONO, download the sample, and then we import it into Ableton to use it as an instrument. We now add just a little bit of light audio processing effect to further shape the sound. And we can record a loop. Next, we'll generate a lead part, and for that, we'll be generating a pluck-like sound. We first look for a plucked string sample, and we load it into NOTONO, and we further shape it. We sharpen the attack, we add some brightness in the higher frequencies, and then we load it into Ableton Live. We extract a short loop from it, we add an arpeggiator, a reverb, and here it is. And to finish up this simple song, we'll be adding a slow pad-like sound. So we started from a sustained string sample, and we shape it using NOTONO. We then load it into Ableton. We again add some light audio processing to make it into a soft, smooth pad. And there you have it, a full song where all of the sounds have been created using NOTONO.
Okay, so I'd like to thank Siran Awama for helping me make this video, a colleague at the Sony CSL Paris lab. And now I'll be getting more into the details of how we actually built this model. So what are the challenges for performing inpainting on audio? So there are several requirements that we wanted to maintain whilst building this model. And so first, we want to build a model that offers good reconstruction quality. So since we'll be editing samples, we want to be able to just load a sample and play it back as cleanly as possible, so without artifacts. And also, we want this model to be efficient, since we want it to be usable in interactive context, and we don't want the user to have to wait a super long time to perform transformations. And then we also want it to be flexible, so it should be able to generate diverse instruments and diverse pitches. And then in terms of the interaction, it means we have to answer several questions regarding the inpainting protocol. So first, you could see that we are operating on spectrograms, but that's not a necessity. We could have chosen to, for instance, operate on the waveform. And so we first had to decide a reasonable domain for the inpainting operations, for them to be intuitive and accessible. And then also we need to devise a scale for the inpainting operations, because sound is typically sampled at super high frequency, at high frequencies, around 16 or 44 kilohertz. So if we were to perform inpainting at this rate, then the user would have to interactively regenerate 44,000 points just to transform 1 second of sound. So that would be completely impractical. So we need to define both a domain and a scale for the inpainting operations. And the solutions we propose for that are the following. So first, in terms of the domain, we decided to operate on male spectrograms, which are spectrograms using male frequency, which is a logarithmic frequency scale, because it gives an interesting interpretation as a multiband equalizer editor. And then we perform very coarse downsampling via the VQ-VAE model, which I will be introducing right after. And this allows us to convert sounds into very compact, discrete sequences. And this gives us this nice convenient scale that you could see on the previous demo, with a very small grid, which gives direct access to the sound, but at a convenient and operatable scale. And finally, in order to have a powerful and flexible model, we decided to use transformers, which are modern architectures for sequence generation, because those models are very powerful and they are amenable to in-painting-based editing. And so the resulting model is the following. The full architecture is here, and I will highlight the different components of it. So first, we have a VQ-VAE-based encoder-decoder architecture, which takes as input a spectrogram and converts it into grids of integers. And you can see here an extract from this spectrogram, which corresponds exactly to those two grids here. And so we have a hierarchical model that transforms a spectrogram into two conditionally connected code maps, where one is actually, I'll get into the details of that after on the VQ-VAE model. So basically, we have a way of transforming a spectrogram into two grids of integers, and then a decoder which takes two such grids of integers, so very compact representations, and reconstructs back the original spectrogram. So then that's the analysis synthesis part. But then we want to transform those grids of integers in order to edit the sounds. And for that, we first have a linearization step, which takes a 2D grid of integers describing a sound and transforms it into a linear time sequence, which is then usable as input to recurrent models or to transformers. So I give details on this linearization step afterwards. And then finally, the in-painting part is performed through those two transformer models. The first top model takes a super coarse downsampled representation and allows to perform in-painting on it by using a masked attention scheme, which I'll again detail afterwards. And then a more refined bottom transformer allows to use this conditioning information and also edit the fine-grained texture of the sound. So we have this full architecture here, and now I'll detail all of those components. So first, some general ideas on the VQ-VAE. It was introduced by DeepMind, and initially for the generation of images. So DeepMind is a team at Google, and it's a standard auto-encoding architecture. So the idea is to take an original media and push it into a model that reduces it in dimensionality, and then should be able to take this reduced dimensionality representation and reconstruct back the original image. So yeah, it's turned for reconstruction. But the core, the key difference with a standard VAE is that the bottleneck, so this small slow dimensional latent space, is quantized. So rather than being a full float continuous representation, it will be a discrete representation. This is done concretely by projecting latent representations onto a learned dictionary. So the model is tasked at training to learn a basis of vectors that will be usable to reconstruct compactly, in a very compact fashion, the latent space of the model. And finally, it's using a multi-scale representation, which is a very nice aspect and that is very useful for our interactive interface. So the idea is that we start from the original image, we coarsely downscale it towards a first image-like representation, and then even more downsample it and obtain another image-like representation. So both of those representations here correspond to, on a higher level, downsampled versions of the original image. And then those two latent representations are converted to very compact, to grids of integers, thanks to this quantization scheme that I mentioned before. And finally, in order to reconstruct the images, the model first analyzes the very coarse latent representation here from the top level, which basically describes the general global information of the image. So it says here it's going to look like the head of a bird, and there, so here corresponding to there, it's going to look like the tail of a bird. And then it gives this information to the bottom level, which is then tasked with filling in the blanks and generating the fine-grained texture of the image. And so here, maybe this square here corresponds to the head of the bird. And then those 4 squares here will say, okay, so I'm going to put a red eye, I'm going to put some black feathers. And finally, we get this reconstruction here corresponding to the original inputs. As for our application, so we are performing, we are training a VQ-VAE on spectrograms. And for that, we are using the NSynth dataset. So we have 4 sounds that are 4 seconds long. Here, this corresponds to 4 seconds of sound. And we are using the MEL IF, so MEL's frequency and instantaneous frequency representation, which was proposed by GANsynth, a model from Magenta again. And we augment this representation with phase masking. So very basically, the MEL IF representation is quick variant of the typical spectrogram, where the phase component of the spectrogram is replaced with a temporal unrolling of it by taking the first order derivative of it. And it makes the usually very noisy phase component more smooth and more amenable to analysis using neural networks. And we use for the encoder and decoder parts, which are performing the downsampling and then the upsampling, we use a very standard ResNet-based UNet-like encoder-decoder architecture. And finally, this gives us 2 hierarchical representations. The first, more fine-grained, is the bottom code map, which is comprised of 64 frequency bands. So on the vertical axis, each of those cells here corresponds to each of the rows correspond to a frequency band, and 8 columns. So each corresponding then to half a second of sound. And the more downsampled top code map is then even smaller, and is only 32 frequency bands and 4 time steps. So then this top code map describes the global envelope of the sound, and the bottom code map describes the finer textures. So we hope it describes the timbre of the sound. And for more details, we train it with a standard L2 loss. So now I'll describe how we move from those 2D code maps to sequences, since we need this linearization step in order to apply standard recurrent or transformer-like models on those spectrogram representations. And so this is required for the autoregressive modeling. And for the top code map, we will look at the sound. So we here, for this spectrogram, we now have a grid of 4 columns and 32 rows. And we'll basically unroll it into a sequence by going through it in order of ascending frequencies. So we start from the beginning of the sound at the lowest frequency, and then we run through the sound, going up in frequencies, and then to the next step, and then up in frequencies again. And basically, it allows us to introduce a conditioning, a dependency on lower frequencies when generating the sound at a given frequency. And so to generate the higher order harmonics of the sound, we will look at the lower frequency content. And for the bottom code map, so here you can see two corresponding slices of a code map corresponding to one another. And here, this cell of the top code map, which corresponds to this part of the sound here, corresponds to those 4 cells in the bottom code map. And so we want to align this information from the global representation, the top code map, to align it with the bottom code map. So the model can then optimally use the information, the conditioning information, when regenerating the bottom, the bottom part. And for that, we then use a zigzag order, which is aligned with the top code map. And it means that we are going for the bottom code map to run through it in this whole order here, going as these here. So we start there from the bottom and we all go up, then to the right, up, and then go up again, which ensures that those 4 cells here are then aligned with this simple cell from the top. And we do the same for the above cells. And eventually it gives us a full sequence, which is perfectly aligned with the top code map. And then the information is tightly linked. So yeah, this compensates for the upsampling and ensures that the conditioning is aligned. Then we perform inpainting. And for that, we use transformers. And general notions on the transformers are that these are attention-based models. So they will learn to attend to positions in an input. So the model will be asked to generate some sequence of information, but for that, we'll have access to another sequence of information, which is the sequence-to-sequence modeling scheme. And there are multiple schemes of attention. Each will guide the model into looking at specific portions of the conditioning information. So it could be full attention, where the model looks at the whole conditioning sequence, or causal attention, which is useful in autoregressive modeling, where the model only looks at past information to generate the given information at the given time step, or anti-causal attention, which looks at the future. So here is a demo of an attention-based model at work. So first, it encodes the original sequence. So here it's doing translation. So it's starting from a sequence of tokens in Chinese, and it's running through it to encode it. And then the decoder tries to translate that into English. And to do that, it will, at each time step, look at a different subset of the encoded information from the original sequence. So here you can see the attention levels. So for us, we had to devise a way of properly performing attention on our spectrogram representations. And for this, we use 2 different schemes of attention for the top transformer and for the bottom transformer. For the top, since it has no external conditioning information, we will be using the so-called, it's a custom Sony CSL Paris name, the AC/DC style attention scheme, which is that we use an anti-causal encoder and a causal decoder. Concretely, this means that we are doing autoregressive modeling. So we are generating frequencies starting from the bottom and going up. So the decoder, which generates the next token, will only look at information from the past in order to make it autoregressive. But then, since we also want the model to generate information that is coherent with the rest of the sound, we want to help we want the model to have access to the rest of the information. And for that, we have an anti-causal encoder, which takes all of the information from the future at a given time step. So it will be all of the above frequencies and the next time steps, and uses also a mask that we can control. And this mask allows to hide the information. So this is the inpainting mask that I mentioned for during the inpainting demo. And so this mask allows us to provide a subset selectively of the information to the transformer. And for generation, basically then, it runs through the frequencies in ascending order, and at each time step also has access to all of the rest of the spectrogram. And next, since for the bottom transformer, we want to make use of the information from the top transformer, which is the conditioning information from this global representation of the sound. We use aligned diagonal cross-attention on the conditioning top code maps. So here, for those 4 time steps of the bottom transformer, we will only use, in order to make it more compact and easier to train, we will only use the information from the corresponding time cell here, code cell here, from the top transformer. So this is what we call the aligned cross-attention between the bottom and the top. And also, in order to ensure that the bottom transformer generates coherent outputs between the different cells of the bottom code map, we also use self-attention. So the transformer has access to the rest of its representation during its generation. And finally, some additional details on those models. We perform autoregressive training, which is very standard, and we use label smoothing, which helps stabilize training. In order to emulate the behavior of inpainting, we randomly sample code maps, the top masks during training. So it's like saying that we have a user which is interacting with our interface and hiding selectively some portions of the image. And we ask the model to reconstruct those missing portions whilst we are training it. Finally, we also give information to the models regarding the time and frequency positions of each of the cells. So it helps the model know that it's generating, for instance, a part of the sound which is at the beginning of the sound and at a high frequency. And it will guide its behavior into doing, hopefully, different outputs when it's generating the attack of a sound or the release of a sound. And we also support global conditioning, as I mentioned before, and you could see in the demo. The interface supports giving constraints such as the instrument type or the pitch of the sound. And we do this through very simple one-hot encodings, which we feed along with the sequences to the models. So then, a quick note on a very related, but actually also very different work from competitors, OpenAI. So this year, OpenAI released JUKEBOX, and those 2 models share a very, very similar framework. Both use VQ-VAEs plus transformers, but with very different goals. And so OpenAI JUKEBOX, which had massive media coverage, and that is understandable since the model offers to perform full song generation, but it's a huge model, and it has extremely impressive quality, and it provides very powerful insights on training VQ-VAEs for audio. But the downside is that this huge model, which has amazing audio quality, is extremely low to sample from. and it requires around 3 hours to generate just a single minute of audio. And that makes it completely unusable in an interactive context. And conversely, our approach is very complex, and it's intended to operate on short sounds of duration 4 seconds. And because of that, it has less representation power, but it's also much more reactive, and it requires, you could see it in the demos, around 1 second of processing time for 1 second of audio generation. And with that, it's clearly designed for musicians, which was the idea from the very beginning, and designed with interactivity in mind. And a note also on the interactive interface that we built. So video plays now, showcasing again the interactive scheme. And we think that this interactive interface is crucial for adoption by musicians. Our models would be unusable if not for a true usable interface. And this interface is web-based, so it's easily deployable and accessible. You could use it with your smartphone even. It's open source, and it's using a simple API, which will be useful for researchers in order for them to integrate their own models. It allows to perform novel sound transformations, such as the multi-scale transformation approach, where one will edit first the top code map and then switch over to the bottom code map in order to refine, whilst keeping the global idea of the sound, in order to refine the timbre of the generated sound. And also, because of the iterated approach, where one successively performs inpainting operations, using different constraints, so maybe using different instrument constraints, one can generate hybrid sounds where, as you could hear maybe in this short demo again, maybe the attack will come from a guitar, and then the release and the bottom part come from an organ. And so it allows for this very interesting hybrid sounds. Some examples of sound generated by this model now, where we started from an original sample from an organ. And then we kept the top code map, which describes the global information of the sound, and we regenerated the bottom map with different pitches and different instruments. So now it's the same sound, but played from a brass, and now at a higher pitch. Now sung and played by a string instrument. You can see that throughout those different examples, the temporal envelope of the sound is very similar, but the texture drastically changes from instrument to instrument. And now to showcase last and very interesting and important aspect of the work that we do here at CSL Paris, that is that we work in close collaboration with musicians. And we think it's crucial in order to investigate and develop the potential creative uses of our tools. Pardon, yeah. So yeah, so yeah, we want to work in close collaboration with musicians in order to ensure that our tools are actually useful for them. And so for this project, we are working with young French-American composer Huel Lamour, who is signed with Sony Masterworks and is working on an EP inspired by video game music using our tools. And the track that I will be playing now, which is called Corruption of the Toad Forest, was not completely made using NOTONO, but some tonal elements of it were built with this interface. And I'll first start by playing the sound that you created using NOTONO by transforming samples from video games. And I play it in context, and that's this sound. You can hear the sound in the background. It's a slowly rising, kind of creepy sound. And now I'll play the full track. And for this track, the idea of UL was to represent a forest. And the listener goes into this forest. And at first, everything is nice and seems beautiful. But then progressively, the listener notices that there are some dark and eerie aspects to this forest. And those eerie aspects were created using NOTONO by taking sound samples from sci-fi video games and transforming them. So that was the sound in the background. I made the harsh cut at the end to shorten it a bit. Now, ongoing work regarding this model. We still have to perform a qualitative and quantitative evaluation of different approaches in order to really assess the performance of the design choices for the architecture. And then different routes for improving the models. So first, we want to try and integrate some recent advances on transformers in order to even increase the efficiency of sampling. So that would be using linear attention-based transformers. Then we also want to improve the reconstruction of those models, and that could be actually helped by this faster sampling approach, which would allow us to have a higher resolution for the models, which for now are very, very costly downsampled, and that might limit the performances of the analysis synthesis team. And we would like to have more diversity and flexibility in the regeneration. So maybe have other constraining information. So that would depend on the information available in the datasets that we have. For instance, regarding those datasets, we'd be interested in training those models on other types of sounds. So maybe train it on a specific synthesizer to help emulate this synthesizer, or train it on real-world sound effects such as gunshots or footsteps in order to design a tool for sound effect designers. And now that's it for my presentation. And I'm available, of course, if you have any questions, maybe regarding more details on the ML part of the prototype, or if you'd like another more detailed demo of the interface. So yeah, feel free to ask. And by the way, all of this work is actually open source, and the interface is available at this link, and the model for Spectrogram Inpainting available at that other repository. Thank you very much for your attention, and I'm here for any questions. Yep, Alessandro.
Oh, thank you, Théis. Your presentation was really very interesting and fascinating. Of course, I don't know if everyone could understand everything because of very detailed description of VAE and vector quantization is not typically very known by everyone. But I think it's very interesting and useful. Just a very basic question. I'm not an expert in all of that, so I think it's really very basic. I mean, when you deal with spectrograms, actually you are using the intensity information of spectrum, but you have to deal with complex numbers. I mean, you need intensity and phases. How you dealt with these complex representations of inputs and outputs, because the VAE decoder should reconstruct the sound from, I mean, this complex information. Thank you.
Yep. Oh, I will share my screen again with a slide on that. It's what I quickly mentioned for the representation. We are using a representation for this that was proposed by Google for another model that they built called GANSynth. And in this model, they were trying to find nice representations of sound that work with convolutional neural networks, which is exactly what we're doing here. And so exactly, you're right, it's tricky to handle the phase component. And that's why they introduced this so-called instantaneous frequency representation, which actually was used before that, but they were the first to propose its usage for CNN-based modeling of sounds. And the idea is you then have a CNN that operates on two different channels. So the amplitude of the spectrogram and the phase. But the phase then tends to be very unstable. It's tricky to model as is. And if not, it's actually unstable almost everywhere. And it's even worse in areas where the sound has low amplitude, because it gets almost noisy, and it's just statistical noise. And then that would be very inconvenient for the CNN to have to model that statistical noise, which is also completely useless because the sound at that point has no amplitude. So it's a completely wasted energy to try and model that information. And so to try and circumvent, they just take the first order derivative of the phase, which makes it almost constant for sounds produced by typical natural sources, because those sounds tend to be sustained, and the phase is just linearly increasing then. And when you take the first order derivative of it, it becomes constant, and it's much more smooth. And we then augmented this representation with a phase masking protocol, where we actually set all of the information to 0. We just ignore it in areas where the sound has low amplitude. And then at the reconstruction step, it's very easy to take back this instantaneous frequency, which has been modeled by the CNN, and integrate it, which gives back the phase information that we can use for the reconstructed sound.
Okay, thank you. It's very fascinating. Thanks.
Thanks. another question. I have.
So, Théis, you're using unit-like architecture for the encoder decoder.
Yep.
But so that means in the decoding part, you need all the skip connections for the decoding.
No, we remove them. It's
Okay.
unit-like in the sense that we just take the encoder and transpose it to obtain the decoder. But then,
Okay.
yeah, obviously, we don't have access to the original input
Okay.
when we're doing inpainting. But that's a reasonable remark, very reasonable. Any other questions? Otherwise, I can give you Word exclusive demo of full computer music using a recently made connection between the two NOTONO and NOTONO prototypes. So we are still not sure about the name for this combination, which would maybe be NOTONO. But here you go. So here I have NOTONO. You should be seeing this. And I start by saying, okay, I'm going to generate a full sound, a full organ sound. I generate it at pitch C, so I'm sure that it's then easy to interact with it afterwards when I'm playing the sheet. So here I am. I just generated a full sound. And then I have here NOTONO. So here you can see the sound. Okay. And then voila, we have full computer generated music. And you can edit the sheet and then the sound. So we think those interfaces would also be very interesting for education because one doesn't need any training in music in order to easily generate both sheet and sound, and so one can generate full self-contained songs interactively without need for any musical training. So we will try and disseminate those prototypes in maybe music schools and conservatories, for instance. Any other questions?
Okay. If there are no other questions, thanks again, Théis, for this great presentation. And see you next week for no, in 3 weeks. We have a break for 3 weeks, and we will have another seminar in 3 weeks. See you.
Bye-bye.